Perfect. Welcome, ladies and gentlemen, and good afternoon. Welcome to the STIA's third session of the week. This is our heat recovery workshop. Today, we see Karl Rabe. Karl is the MD of Colocation.Green, and he'll be talking to us about integrating energy into the future of high-performance computing. So, Karl, if you want to just open up on that topic for 30 seconds.
Yeah, thanks so much for inviting me, Mohan, and STIA cooperation or alliance. I'm very happy to have a group of people who now are fighting with us for sustainable IT. Thanks.
Perfect. And what I'll do now, I'll just talk through the audience, the sort of house rules. Please post questions, and please feel free to use the chat. You should also see the handout section, which is where you can actually download the slides. So Karl's slides are on there for you to download. What we'll do is we'll start the video now, and then we'll take questions at the end. Okay. So Karl, if you mute yourself and remove your camera as well.
Yeah, sure. Just.
Hello and welcome to the Colocation.Green talk at Sustainable Places 2020. You are at the STIA track. Hi, my name is Karl Rabe. I'm the project lead and sales director for Colocation.Green. We run sustainable IT infrastructure in a wind farm and are excited to share our insights and knowledge. Let's get started. What I'm going to talk about, you just heard, I'm an engineer by trade, lots of experience in the IT world, a couple of companies founded there to actually get sustainable IT off the ground. After that, I'm going to talk about how and why we measure CO2, especially in data center, how we enable sustainable HPC, and how do we recover heat. Personally, this is my third kickoff for sustainable IT infrastructure. We started off with a company called Windcloud and Birger in 2015. Had a nice energetic setup, storage battery, wind farm, biogas backups. But the grid configuration and the grid operator made it impossible for us to go through at that location. Due to the loss of location, we found another Windcloud company, which is Windcloud 4.0, which is now still active and present, running under the Windcloud.org domain. They too want to offer sustainable IT infrastructure, just go down a different path. And today we focus on Colocation.Green, which is directly hosted within the wind farm and just allows for massive scalability, the best energy prices in Germany, and a special approach to data center building. There were some learnings, there was some progress over the time. So we definitely increased our energy supply and the approach and how to get more and more sustainable energy into the data center over the time. And we, needlessly to say, we're massively improving our data center infrastructure. We started off Windcloud Birger with a old and rusty shipping container, which we modified with only the technologies we understood. It had cooling, it had fast internet, and that was about it. At Windcloud 4.0 we built a proper ISO certified and in the meantime EN 5600 certified data center infrastructure, and all those learnings we are now improving and building out at the Colocation.Green facilities and locations, and we are creating modular data centers, so no shipping containers anymore, but low footprint approach to house and host massive amounts of sustainable infrastructure and HPC computing. What hasn't changed, the underlying idea is always get the massive amounts of wind capacity installed in North Germany and create sustainable and competitive IT solutions with it. Just as a very brief sum up of this picture, IT operations, data center operations, the internet in total is a massive source for energy consumption, greenhouse gases, and e-waste. All the buzzwords you've ever heard, all the buzzwords that are flying around, new and old, are creating trends that demand for more data center capacity, for more IT servers and equipment to be run in those data centers, and those all are growing at a rate that is actually being predicted that data center usages will be the largest single IT or source of CO2 emissions by 2030. This is just a slightly different variation of all those problems together. We're looking at an exponential function, and we are much rather moving towards the red line within all those predictions on how the digital energy consumption is evolving. So we really need to act. How do we measure CO2? Since we are at the sustainable places, I'm sure that people are familiar with the three scopes. Here's a nice example I took from the Green Web Foundation, which I highly recommend you to check out, because they are even talking, I think, in the SDR track as well, and they have made a lot of efforts to look into and to go through to get your footprint in IT down. Scope 1 basically is everything a company burns directly in fossil fuel. Scope 2 is the energy, and Scope 3 is your supply chain, which is the most discussed at the moment, because that is still quite very difficult to figure out how to really reduce this. How does this look in a data center? Just briefly, first of all, we run our backup generators once a month for maintenance, which is accounting for CO2. Obviously, we looked heavily into how to solve Scope 2, how to use renewable energy directly for the IT equipment and without using fossil-based electricity. We moved our IT to the renewable sources. Scope 3 is everything we as a colocation provider are doing, basically anything else, from construction of the data center, from sourcing of materials, from our traveling to fairs and customers. All those is falling into Scope 3. What technically is a bit challenging is the service. Since we are a colocation provider, is that the CO2 amount that goes into the servers is not really associated for our operations. We have already looked into solutions, and you've heard probably here already solutions on how to fix this from Ali from IT Renew. But this still remains one big issue in the CO2 and the overall CO2 emissions of IT application usage and IT operations. Just some numbers. So fairly easy and quick evaluation how our carbon emissions are distributed over the scopes. Scope 1 is fairly small. Scope 2, the energy is a mixture of wind energy, which is accounted for 11 grams per kilowatt hour, plus the 5% we have to consume from the grid. So in combination, we face about 22 grams of carbon per kilowatt hour. And scope 5 is basically the construction of the data center infrastructure, plus travel, plus everything we do over the course of the data center, over the lifespan or estimated lifespan of the data center of 15 years, divided through the total consumption of energy. So this depends obviously on a lot of factors that are not totally fixed, especially hard to predict in the beginning. But this is a fairly high value for what we're doing here. So compared to the German average of energy mix, which is the value I just looked up this morning, of the actual energy production in Germany as of today, we save a massive amount of carbon per kilowatt hour. But this does not make us carbon free yet or carbon neutral. It just presents a massive reduction that we also communicate towards our customer, that we also, with every bill, we will also have the savings accounted for as in our billing systems. So how do we actually solve this? The last bit. How do we come to carbon neutrality? Since we are running HPC systems, which we hear on the technology later about, we have the possibility of reducing the heat. This is the actual big beneficiary of HPC technology, because the CPUs and GPUs are not ideally cooled by air anymore, rather than water, which gives us a high level of temperature and massive amounts of kilowatts in heat. And by the 70% that we can actually use of the energy, we emit the fossil burning, for example, for using our heat to dry wood chips or to use them in a heat grid. We avoid fossil energy being burned, and if we add this into the mix, then our carbon emissions, which we are not free of, are compensated by a value that even makes us carbon neutral, and even above that, slightly carbon positive. So this is the math behind this, but how do we achieve actually this reuse of heat? Why are we moving into co-location? Why do we want to be a co-location provider? Gartner predicts that from today until within the next 5 years, 80% of traditional data centers will have closed down their data center. And this is a massive opportunity for us. Partially, these workloads will go to the cloud, partially and mainly, we hope, they will go to specialized colocation providers like us to be able to grow quickly and start off new locations and further megawatt deployments for our data centers. Why do we work so hard to create a cost-effective product in Germany? So basically we are located here in north of Germany, and just 30 kilometers away from us, behind the Danish border, is the so-called 5 cent region, which stands for the Nordics, that have a massive growth in the data center industry, because all of those green highlighted countries offer sustainable energy below 5 cents per kilowatt hour, and this is where most of the HPC projects move. So we just go through great lengths to create data center services and products that are so attractive that we still are able to get some of those industries, hold them in Germany, and get them actually being deployed in Germany. This is our setting. This is another view from our data center locations. You see here on the right 8 foundations for data center modules. They are ready to deploy, and a switch yard for 300 megawatts. Each of the 80 plus turbines has over 3 megawatts of capacity, and so they all are combined, create a total capacity of 300 megawatts within this switch yard. This picture is nice too in some other specific ways. One is I've actually grown up in this location back here. We see the North Sea here, and we already have heat use cases very close by. In this direction we have a pig farm, crop dryer, and a biogas plant with their own heat grid. We will also build a heat grid in the other direction to the next village, which also has an existing heat grid for our energy to be used. This is our electric setup, which is quite unique. So what allows us for the best, having the best electrical energy price for any data center in Germany, basically is due to a new mode of grid operation where the wind farm, the wind producers also become their own grid operator. This is the transformator in the middle you just saw on the picture ahead. But what is happening now, the wind farm also is operating its own grid on this 20 kilowatt level, so that the energy is transmitted via its own grid. And by running your own grid, there's some advantages, including that you are able to supply energy to any commercial company. So this is represented by us, by Colocation.Green product. And the benefit for actual data center operation is that our switchyard is connected to 2 redundant 100 kilovolt settings to the standard grid. So even if we wouldn't have any energy operated, we still have the chance to keep on running the grid over one of those backplanes. How does our setting look like? So you saw on the picture, you saw 8 foundations. We've already projected 5 of those, standard business IT and an OCP module. Those are air-cooled bays, which we just briefly touch with pictures. This is, your standard 5 kilowatt density, not that exciting, just very redundant, all the bells and whistles and certifications. This is our HPC module that is directly water-cooled, direct to chip, and the other HPCs are immersion cool module, where we are using tanks to run our workloads in. So this is the standard business modules, redundant data centers for maximum availability and security. This is the OCP module with lots of cooling because of a relatively high rack density, which still needs to be air cooled. And now we jump into the HPC modules. This is our direct-to-chip HPC module, where you can see here nicely that there is still cooling modules installed because we cannot reuse the heat at all the time. Additionally, there's still air coolers on top, which means not 100% of the heat created is moving into the water for cooling. There is still fairly high share that needs to be cooled via air. So this explains the setting. And the immersion module, which we have not fully designed, but will be looking like a similar module. I just wanted to show you how those tanks look like. Those tanks are connected at a very high temperature level with a fairly easy redundant pump and moving to a cooling solution. So you basically never need to create artificial cooling to cool those down, because they can run at a relatively high temperature level. This is the view inside one of our data center modules. You'll notice that there is not only compute modules in here, which are paired with 4 racks each, but also a storage part, a management rack, and a UPS to buffer the storage in case of an energy outage. On the right, you see the central distribution unit, which distributes the water through the racks and out to the cooling. Very important that these redundant pumps, these are the pumps to make the energy usable for the community heat grid. The heat energy is transferred out to the heat grid and coming back as well here, and this way the energy can be used. Here you have our quick look at the water cooling setup. This was the CDU we just saw. This is the circle to the individual racks, coming back at a temperature level of 62 degrees, which will go over a heat exchanger out to the cooling units at 57 degrees. So depending on your temperature this is you can expect temperature around 60 degrees to be usable for any application. We already have, as I showed you, community heat grid, crop dryer, the pig farm, as well as the whole area around this switchyard will be becoming a commercial area, which will be the only commercial area in Germany who offers renewable energy at best price and renewable heat. This is a first in Germany, and I think that will be very attractive, and we won't see any issues in reselling our heat in a very close proximity. How's the actual cooling done within the racks? Here you see a typical water-cooled server, 4 CPUs each with copper cooling plates that are supplied with cold water, each individually on all 4 nodes. So they're not one after each other, so the temperature is not raised from the first CPU to the 4th, but they all get the same cool water flow in parallel, which helps to get the maximum performance out of each CPU. And the hot water is then moving out within a chassis like this, and here you see a manifold which connects to 6 of those servers, and they all then combine in the back of the rack and going out to the CDU. So this is the way how the energy is actually moved from the chip, from the RAM, from components in the front of the servers out to the piping to the central distribution unit and then the cooling. So let me just go briefly, just as a reminder for us, how we are, if I've missed something, or what are the features that we actually can do. Renewable power, massive scalability, all the certifications. Right. Okay. So to sum this up quickly, we run data center modules in a wind farm, creating circular energy systems, and have the massive potential to reuse heat in the data center, and by thus creating a sustainable eco data centers around our data centers, at the plus that our customers can expect the best sustainability for any data center in Germany, a high profitability due to very efficient operation modes, and effective and efficient operations for HPC, and the best data center designs for the application. And with this, I'd like to thank you, and I'm open to questions. Thank you very much.
Thank you, Karl, for that presentation.
Sure. Let me show you some business plans where people...
We might need to mute Jens. Okay, thank you, Karl. So we have the first question here from Stefan Frenzel. He says, great presentation. Quick question. Why should I, as a potential customer, join your site, apart from possibly the legal advantages and not choosing a co-location site in Scandinavia? So I guess it's a summary of what you just said, the benefits. What are the benefits of your site over other sites?
Yeah, thanks for the question, Stefan. So one of, if obviously the combination of the three, let me put in the video maybe again. So hi, I'm back. Yeah, thanks for staying with me. So other than the combination of sustainable, legal, and cost-effective, there is actually a very limited number of operators who have the possibility in combining water-cooled, immersion-cooled, and high-density air-cooled solutions. And this is basically a technical flexibility we are able to offer. Plus, we are not fixed on the co-location modules that are based there. So we offer any co-location provider, and there are quite a few, to move in our site and become basically becoming a North German data center location provider. And that is a flexibility that we offer to the customers.
Interesting. And is that live already? Have those sites been built and you have customers already? So
we are in the sales process. We've been limited by the availability of the energy, and that unique grid setting I was talking about is starting on the 1st of January, and we will move in with the business IT units in February, and the HPC, the first HPC module, will be announced and live or presented at the ISC next year, so in June. So fairly lots of work still to be done, but a fairly quick time compared to the time spent in working on this. And we have the option that actually we have some inquiries of people wanting to come in with a module. Some of them are actually existing, so we can see active operation as soon as the 2nd of January.
And can we go through that grid arrangement again? So you have your own little mini grid, and you use the wider grid as a redundancy. Is that correct?
Yeah. So I'm very happy of having real experts and consultants who are fiddling around the details in this very unique grid operation. And the legal depth of that is beyond me. But the intergrid regulations allow for the time that we don't have actual wind energy, for still allowing us to be supplied by the public grid and not falling back into the special German grid and renewable energy surplus. So that is a nice benefit of running their own grid. The wind farm, why is the wind farm building this? They are not only building this for us. They benefit from having their own grid because they move the monitoring and billing from the central switchyard, from the picture you saw, from the central out into each individual turbines. And by doing so, they reduce the roughly estimated 2% losses from the wind turbine to the switchyard. And so the fee, the grid itself is already a very attractive model for them, just because they optimize the production. And the plus is that they are able to supply commercial customers. So we are happy to benefit from that.
Okay, fantastic. Now we have a question here from David. So Giuseppe, if we want to unmute David so he can ask his question.
Yes, can you hear me?
Yep.
Yes, hi.
Okay, perfect. David? Okay.
Hello, yes.
Yes,
You hear me?
Perfect.
Yep.
Yes.
Hi. My question is, you show wasted with high performance racks, but didn't show this waste using with immersion cooling. What's the reason of that?
So basically is that we, well, the easy answer is we are not finished with the design of that module. So just was able to show you a quick overview, and there's actually quite some interest for this solution in trying to get more efficient performance out of existing hardware, and the necessity to reuse the heat. But unfortunately, we have not fully designed and spec'd out this solution. We are in active discussion with the server manufacturers, with the tank manufacturers, on how to do this the best possible way. But I have only have very limited details to share with this. But one important or exciting factor while using tanks is that you can achieve an even higher temperature level, going from roughly 60 degrees for the direct chip up to 70 degrees for some applications, and that's why we want this application at our site.
And can I ask another question?
Sure.
Do you have any thoughts about using the waste heat from air? I mean, use big heat exchangers which can achieve outside outcome with 30-32 degrees.
So let me get this right. You're asking for
you said that still some part of high performance rack is cooling by air, and
yes.
This air is not possible to reuse. And my question is, didn't you thought about air heat exchangers which can heat up the water up till 30-32 degrees?
Okay, I understand where you are, where you're getting at. We didn't think about it. Just to be brief, I think it is an exciting possibility in terms that we actually have shortage of energy and be able to reuse, to squeeze out, the extra 10-20% of energy for this for the solution at this time. The projected energy that or heat energy that people actually are willing to take off our hands is roughly about 1 megawatt. And if we put those two, the immersion cooled system and the direct water cooled system together, we have an excess of about 1.2 megawatts of energy. So at this point, and that is over the course over the next 4 to 6 years. So we have a massive excess of energy, and therefore we did not think about reusing the air in our solution yet. But if that would be to change, that could be a viable option in becoming more efficient in reusing the heat.
So you've spoken about their a sort of a more efficient electricity architecture. Can you go into detail then on the heat architecture that you have? So because it looked like there were a couple customers in the local vicinity, but how much heat infrastructure do you already have down? How much was there before? How much have you added, and how will it grow over the years?
So there are, as I said, there are two existing heat grids. That the one that was in the picture is fairly small. It's only 4 farms, the pig infrastructure and the crop dryer, which is very easy to connect. It's about 100 meters to build out to connect to this one. In the other direction, we actually have to build out quite a bit of energy. Or quite a bit of energy grid, which is about a direct line of about 800 meters we have to build to connect to an existing biogas plant, and that biogas plant is then connected to the village. And the existing community heat grid of the village has a temperature level of about 85 degrees. So on top of the 800 meters of grid to be built, we will also need an heat pump, right? I think it's a heat pump to match the level of temperature. But because we have cheap energy, it's actually viable to do so and support the existing biogas plant infrastructure, because the heat grid is right now under extension. So I think currently there are 40 households connected to it and a big recreational facility, or actually 2 big recreational facilities. And over the next 2 years, this community wants to connect another 100 households to it, plus 2 more commercial properties. And this is something that we nicely can use, but there's some more heat. There's some more work to it than just plug and play.
Yeah. And you, last question from me. You mentioned that there was it sounded like you said that there would be a commercial development around the switchyard. Specifically, sort of. I mean, would they plug in and play with?
Yeah, we would hope to, we are developing together with the community of which is another community than the village. So the wind farm is its own community, and those were all farms. You saw the pictures. You saw this is the whole community is owned with farm after farm after farm, and we had massive problems in actually deploying a data center because it's not an energy only business, and so we needed this commercial area in addition to the farms. And so we're now developing together with the community also the heat standard and the energy connecting standard for businesses who are willing to move around that. On top of the heat we have, those are very forward-thinking farmers that moved into becoming, energy entrepreneurs 30 years ago. And if you offer them cheap energy of any kind, they will come up with exciting new use cases. So greenhouse usage in a farming perspective is interesting. Fish, indoor fish farming, specialized vertical farming applications. Those are all things that are now discussed in the minds in this community. So there's a commercial process use case, but also the agriculture use case is still very interesting for them. So there's plenty of options in using the heat, but it's not. We unfortunately, or unlike my prior company at Windcloud, we built our own Algae farm, which is just nice to show how to use this. But here we have so much to do with the different data center infrastructure that we are only, we supply the heat, we support, the allocation of grid, but we are not capable of using it ourselves in any kind.
Interesting. And so it sounds like there's quite a lot of stakeholders then involved in this project.
Yeah, absolutely. Which is a plus and a minus, and as in any case. But the beneficial part is that this is a community-owned wind farm. So all the farmers, all the mayors of the communities, they're all involved in energy, and they all see an issue with the excess of energy we have and the little of energy we can use. So by us going in there and being able to potentially create megawatt demand of energy is a very political positive issue, and everybody is greatly supporting an industry build up and an energy demand build up in the north of Germany, because basically we're all only farmers and fishermen up here, and there's no real demand.
Okay, and last question here from Stefan Frenzel. When will you reach scope 3?
Well, scope 3 is obviously the tricky one, and I'm greatly appreciate that now, also especially due to the combined exchange with the Sustainable Digital Infrastructure Alliance, that I actually have options in looking into, and we are in discussion with IT Renew. We are thinking, we connected with eco data centers who are building data centers with a lot of wood to reduce the CO2 footprint. So we're looking into all those options, but I don't have a date yet, unfortunately. Sorry, Stefan, but we are in a development project for a wooden module, if that is, so to say, something exciting for you. Probably, maybe we can announce this next year.
Perfect. Thank you, Karl. I'll just give you the last sort of 20 seconds to say, again, where people can read up more on this, or where they can contact you, and then I'll move on to our next speaker.
Perfect. I would like to thank everybody again, the Sustainable Places, and Mohan, Lasse, and Max for this very interesting track, and I'm very excited to listening on the other people talking about how to recover energy. And feel free to reach out at over Mohan or me at Colocation.Green. Bye.
Perfect. Thank you. Now I'd like to introduce Jens. Dr. Jens Struckmeier is the CTO and founder of Cloud&Heat Technologies. Cloud&Heat is a company that works in the southern part, in Dresden, in Germany, working on a lot of the direct on-chip liquid cooling technologies, among a few other technologies. So Jens, welcome. I wonder if we if we can get your camera on, and could you just say a few words, introduce yourself to the audience before we play your presentation?
Yes, Mon. Thank you very much for the kind introduction. Yeah, so I'm a physicist by education, and energy efficiency has always kind of been a very important thing in my life. But I have done also nanotechnology and working with large amounts of data. So I always was kind of using IT infrastructure as a user, not caring too much how that has been done. And when I moved to that topics 12 years ago, looking at kind of the energy consumption of data centers, I was a little bit surprised how, let's say, old-fashioned the infrastructure there is. And I personally built kind of a passive house for myself with solar systems and tried to optimize the energy consumption of the house. And I was surprised how little has been done on traditional data centers. However, there are the hyperscalers who did a great job in optimizing a lot of things. So we kind of came up with this idea of having servers not only hyperscale on one location, but put them basically where the people are in the houses. And when I do this, then immediately what we've seen in the previous talk as well, then you can make use of the heat. And that's kind of how we started with this idea of founding Cloud&Heat. And what we actually proposed 10 years ago was the idea of really edge computing. And I had to learn that it's a quite conservative world, days in the world. So it took some time to really bring this idea into markets. And I'm happy we have done really nice and interesting projects, which you will see a little bit in my talk then later on.
Perfect,
so,
brilliant.
Great to see that you have this format where you bring this actually to life and to awareness to the people that there is a lot one can do. And there is a transformation going on actually in the data center industry.
Yeah, exactly. That's the aim. Okay, so if you'd like to mute yourself and close your webcam, and we can play the video.
Hello, my name is Struckmeier, and I'm founder and CTO of Cloud&Heat Technologies. In the next 25 minutes, I'd like to give you an introduction to sustainable data center infrastructure and to solutions we have developed over the last 10 years. So, sustainable and secure data centers with heat recovery, that's the title of today's talk. And I will drive you through a journey. What is the motivation to think about these kind of infrastructures and what will drive the future, how we call it, of compute? First of all, let me quickly introduce myself. I'm a physicist. I founded the company 2010, and we have now more than 90 employees, mainly working in Germany, but we now also have offices in the US, in South America, in Dubai, and we have installations in Japan. So what are the big challenges we are currently facing? One big challenge is growth, and we'll come to that in a little bit later. So if you look at the technology, how it's evolving, we will see that digitization is basically everywhere. You see that robots are coming more and more into daily life. We see that the car industry is changing towards autonomous driving, and it only becomes possible with a massive amount of data processing and computing technology. We see new mobile standards come up, the introduction of the new iPhone and other phones that now support 5G and ultra-fast internet connectivity. And this is needed for virtual reality, for new applications that basically come up. We see also that traditional fields like farming and so on is changing due to the new technology coming up. And of course, that relates to our body and our health. The digitalization in the health industry is rapidly moving on, gaining more and more information, understanding more and more how the biophysics works and also how the body works. That drives a lot of information and data that has been compiled. And there are also technologies that come up that nobody has thought about before, and suddenly they are there. Technologies like blockchain technology, So others will certainly follow, and certainly there will be a new need of computational resources. So the next big challenge is the challenge security. So if we have a lot of data that we are collecting and that we're processing, we have to make sure these data stay protected, and that people who generate this data or have value on this data, or even have property have the rights of this data, that they know where are the data, and they even can decide if the data stay there or will be deleted. And the other thing is you want to prevent others from stealing your data. So protection of the data is also very important. So encryption plays a major role here. So that's also something that we as our company are addressing if you're talking about the future of compute. And we are active in various areas here, from certification to setting a standard how data center can be certified. We do that in the Auditor project. And there are ISO norms where data security plays a major role. And this is a chance also for even European players to play a major role in the new future of digitalization. Now, the third biggest challenge is sustainability. So we have an increased amount of data on the one hand side. On the other hand side, we want to drive our society to a carbon neutral society, the latest 2050, and get as much done as possible by the year 2030. And there's a conflict here, and I will show you that in a second. If we look at the energy demand of data centers, we will fastly recognize that the energy consumption for data centers in Germany alone is raised from 2010, about 10 billion kilowatt hours per year, to 2030 to almost about 30 billion kilowatt hours per year. So that's already a factor of 3. That's Germany alone, and Germany is not the main country for data centers, as you know. There are other countries where the growth is even much, much higher. To also illustrate the immense energy demand of data centers, you can look at certain examples. For example, an example where you train a robot to solve the Rubik's Cube. So with doing that with trial and error, this requires 2.8 gigawatt hours. And that caused the emission of almost 1,282 tons CO2. So just to get a vision of that, that's 1,500 round trips from Berlin to Chicago. Massive amount of computing data if you approach those problems with massive computing power. So the driving energy demand of data centers is there. On the other hand, this electricity that is used in data centers, that's all converted to heat. And this heat typically is cooled down with air conditioning systems needing additional electricity, right? So, so if you consider the energy consumption of a data center as some heat generation, you have waste heat of about 3.5 million tons CO2 a year you can save if you can use this heat. On the other hand, we see that there are enormous efforts in getting the energy demand of buildings down. So here I have statistics how the energy consumption for buildings kind of goes down over the years between 1996 and 2015. And we see that indeed the private households consume most of the energy for heating. So we see there's a trend here to go towards carbon neutral, but there's a long way to go. On the other hand, we have to look at how you generate then the energy in the future. If you want to heat the buildings, you have to generate that energy. And this graph shows how much percent of the energy type is done renewable already. And we see the blue line is the electricity. So electricity has the renewable percentage of renewable energy in electricity in Germany has raised now up to 42%. But the renewable part of the energy that's used for heat is only 14.5%. So most is indeed fossil fuel that's used to heat the building, and there's only a little bit synthetic fuel and synthetic gas that supplements that. It's even worse if you look at a petrol-driven car. Only 5% of the whole transportation system is fueled by renewable energy. So hopefully that will change with electric cars. but using petroleum to heat the houses. So that should change as well. And of course, one way is to go to heat pumps so you can use electricity. But the other way we will show here is to actually reuse the heat that's generated by other factors, mainly data centers. So we have a map of Frankfurt, and all these little red dots you see here, these are locations where data centers are. As you know, Frankfurt is one of the main data center hubs in Germany. And if you look at these dots, these data centers produce energy that could be used in the surrounding area, basically, to heat up Frankfurt. So this is untapped potential that is there in the cities. And as of today, so far, almost all data centers in Frankfurt, except a very few examples, are not using the heat. They are putting the heat into the air of the city, which brings the major and all the others in the city to the big problem, how to get this city carbon neutral by 2030, which is a goal that Frankfurt had set itself. And then you see newspapers all over the place that say, hey, some of the judgments of how the electricity consumption will evolve is actually wrong. So it's underestimated that the electricity consumption will go up. And part of that increasing of will be digitalization. On the other hand, we see that the European Parliament enhances their goals for climate change and say that till 2030, we want to reduce the climate impact by the factor of the CO2 emission. We want to reduce the CO2 emission by 60%, which is quite a word. So now let's have a look at these data centers. And as I said, it's actually growing. This is a worldwide assumption how the energy consumption of data centers will rise. And you see the data centers as the green block here. You see about also what the consumer devices, how they evolve. They will get better actually, because they want to have a longer battery life. So you put some of the workload also into the cloud. And then you have the production of ICT, so building the devices. So we're talking now more and more about circular economy. So that's an important factor to get the energy amount for producing these devices, getting that down. But as you can see, the prognosis is not it's getting down because you need so much more devices. And then you have the network part. Also, network nowadays is almost computing, right? So you have these massive switches and the wireless stations that kind of connect to the smartphones. So all those need electricity. So we look very much into that. First of all, how can we lower the consumption? That's the first step. And if you've done everything to lower the consumption, the next step is it's converted to heat. So why not using that heat? So that's what we're doing. So let's look at the data centers. So we see the data centers here, and we see that most of the energy goes to the servers. That's of course no surprise. But then you see that's a big chunk that goes to cooling. Well, that can be reduced if you do it smart, right? Also with the servers, you can see where the electricity is going. And we look at this closer, you would see there's also electricity going to fans. Why not removing those fans so that you get this down? Storage has computers in there, so you can do something similar like you do with servers. And then you have uninterrupted power supply and net and other network solutions. And for those, you also want to lower down the energy consumption. So if you do that, that you remove the fans and you put a certain way of liquid cooling, and I'll show you how we do that, onto the servers, you can actually reduce the amount of electricity to cool those servers quite a bit. Now, once you have reduced that, as I said, now you can use the remaining energy that's basically used by the server. You can use that as waste heat. And in a lot of places, you can make use, especially in winter, of the heat that comes from these servers, substituting heating demand of the building. So in order to do so, you have to certify, of course, the use of this heat. And we kind of managed to get a certificate that this heat that comes from a data center can be regarded as avoided emissions on other heating systems. So the primary energy factor for heat that comes from data center can be set to 0.0, and this gives the planner of buildings more room to build an efficient building, taking into account that servers are in that building, and he can reuse the energy of those servers. Now that's something one can do, but I want to show you also what currently is done in classical data centers. So you have air cooling. If you do that right, you have a cold aisle and a warm aisle, and you have a circulating air, and you have systems that cool down the air, and with the system, an air conditioning system is typically connected to, right? There are systems where you have so-called side coolers, so put coolers next to the servers, but still you need compression systems, so classical air compression systems to take the heat out of the air and then bring it to the outside. And especially in the summertime, you cannot do that without extra electrical energy. New technologies evolve, like immersion cooling, where you basically dump the whole server in a liquid and in a non-conducting liquid and cool it with this. So it has really some advantages, but there are also complications with it. It's quite expensive. And there are solutions out there that have been developed over decades now, and we've picked up basically this development, brought it further to direct water cooling, meaning you bring really a cooling loop to the CPU, to the chips, and you pipe the water across this cooling infrastructure, across this heat exchanger, and very closely to the chip, you extract the heat. And that's basically a secret we are doing, extracting the heat directly from the CPU. And then, of course, you need a pump and a pump group with redundant pump and a heat exchanger to have a server rack where a circulating water loop is generated to cool down the servers. And this heat now can be extracted, and it can go now to the building. It goes to a buffer tank, for example, and this buffer tank can be hooked up to the floor heating or to the warm water supply of the building. And if this buffer tank is fully filled because the heat is not needed in the building, this warm water comes back here. And if it's too hot, basically you switch this motor, and then the hot water goes outside to a dry cooler in a closed loop circuit, and the hot water is then cooled down to a level that's acceptable for the servers. Now, cooled down means, in our systems, the server needs a temperature of 55 degrees Celsius or lower, and that's cold enough to cool those servers. I'm talking about 55 degrees, so that's typically hot water, right? But 55 is cold enough with our technology to cool the servers. And the servers heat up this water from 55 to 60 or even higher. And this 60 degrees Celsius is hot enough, right, to be used in a lot of applications and not to be considered as waste heat. If you have just warm air coming from a server, that has literally no value. You want to get rid of that, right? But if you have really hot water coming from the server, it suddenly begins to have a value because you can use it for other things. Now, how do we do that in detail? So this is a server blade that consists of 2 CPUs, and we removed all fans on this server blade. So we put a piping on here with our partner Macware, and these servers are now cooled with the water that comes in here. So you have a quick connector here for electricity and a quick connector for water. So you slide that into a bracket chassis, and it connects automatically to the water and to electricity. So it's pre-filled, and there's a non-spilling valve here so that you don't have to mess around with any kind of water stuff, because it's kind of pre-filled and a quick connector here. So you connected it, and then you get the heat from the memory components here. You get the heat from these components on the back side of this server. These are all the InfiniBand or Ethernet chips that are cooled by this cooling loop. And then the water flows further to the first CPU, the voltage regulator, to the second CPU, to another voltage regulator, across the SSD drives, and basically gets out of the server. So with this kind of setup, we remove all the fans. So that makes this server very low noise, but we also have a very, very slim and compact way of cooling these servers. So why have we chosen to use water as a cooling medium and not air like typical other companies do? Well, the main reason is that air has really its limitations. If it comes to a lot of power, it's very hard to cool that by air. And we know that from the car manufacturer, right? When you have the Porsche in the 90s, they get more and more horsepower in the Porsche. But at some point, they couldn't cool the Porsche good enough. So they switched from air-cooled engines to liquid-cooled engines, and then they could increase the horsepower. So that's something that has been done in the car industry in the past. And by the way, it's done today as well. Like Tesla also is cooling everything with water because it's more efficient than with air. So just a comparison, if you have a data center of 1 megawatt and you cool that with air, and here are some numbers, but it means you need 84,000 liters per second of air to cool that 1 megawatt data center. If you use water, you only need 24 liters per second. So that's a massive factor of 3,500 between air and water. So it totally makes sense to have a closer look at water, despite that people fear water electricity is a dangerous thing. So that's something you have, or we have addressed. So we are using hot water, 4 times higher energy density. No, so that is the number of if you have a regular server, you put water cooling in there, you can basically literally crank the space to 1/4 of the space you needed earlier, because you don't need space for the air coming through and so on. And that's even not optimized. You can even have a higher factor of energy density, as we have seen earlier. You can build servers that need no air conditions anymore, right? And you can do a direct heat recovery. Once you have the heat in the water, it's much easier to transport it and bring it into the building where it can be used. And we don't need any fans anymore. So that gives us a 10% extra energy saving by removing those fans. If you have a data center that's liquid cooled, you can place it now next to a building and have it like a local district heating system. You can place it in industrial buildings. You can place it in cities, for example, in a container next to buildings if the space is difficult here inside the skyscraper, or you can have the data center inside the skyscraper and make use of the heat. And we'll see an example in a few minutes. So the last part of my talk, I would show you some use cases, what we have done and what can be done if you really think about the future of computing and the future of data centers. So this is an apartment building that has been built 5 years ago in Dresden, 56 apartments. And in the cellar, we basically placed our service with our heat recovery technology. So you see the piping here. This is all liquid piping. So we let little air here, but the rest is really direct water cooled. And we have 56 apartments that are basically heated with the waste heat of these servers. And we did this together with a local energy provider. So if you want to have a look later on at the hydraulic scheme of this data center, you can have a look here. So we have direct water cooling, and we also have a certain part of hot air that comes also from switches and other components in this data center. So we also integrated a heat pump to make use of the remaining heat losses from electric cabling to some switches, and that part of the heat we can also recover, and with the heat pump put that also in the hot water circuit. We have buffer tanks so that the servers who run at night basically can provide heat that's then needed in the morning when everybody of this apartment complex is taking their shower. So these kind of things can be used. And the good thing is this apartment complex has not a lot of heating demand because it's insulated very well. It has been built at a very modern energy level. But all year round, you have the warm water usage. And to my personal surprise, the warm water usage in the summer is even higher in the winter. I don't know why, but I can only guess that people shower more often in the summer, and maybe they don't shower ice cold. They shower at least with lukewarm water. So it needs apparently a lot of energy also in the summer. So another example is with the energy. They have a glass fiber network where they put these racks into their office locations. It's lower noise, and they could heat, for example, the warm water for canteen into their facilities. Now, one more famous use case is the Euroteum. That's the skyscraper in Frankfurt, and has been the skyscraper from the European Central Bank for almost 10 years. Now, the central bank moved out of this skyscraper, and they allowed us basically to take over their infrastructure data center that has been in the skyscraper. The 7th floor and underground floor is a fully replicated data center infrastructure, but it was not very energy efficient, and it was being cooled by massive air conditioning systems on the roof, which came now with the new hotter summers come to its limits. So we took over the data center. We said we will put our data center inside that building if we are allowed to access to the heat system of the building, so allowing heat recovery of our servers. So the owner agreed. That was the Commerz Real, and we were very happy because now we could install and renovate the data center, put liquid cooling into the data center. Now we can pipe the waste heat of the service into the heating system of the building, and in the winter we basically supply heat demand to that building. And in the summer we have 8 floors of hotel up in the skyscraper, so we can provide warm water for the spas and shower purposes for the hotel. And of course, there's a sky bar, the only sky bar in Frankfurt. And the barkeeper wants to wash the glasses and sometimes needs some warm water. So that also can come now from the service. And of course, needless to say that there's a lot of cooling cost you can save just by not needing the air conditioning up in the roof, but also the heating cost can be reduced. And these are quite impressive numbers with 198,000 euros and 65,000 euros for heating per year. So that's quite a bit. And there's also an efficiency value that you can calculate how this looks before the renovation and after. And before the renovation, we had a PUE of 1.92, so that means a lot of energy was wasted. And the new PUE is 1.72, is 1.27. So that means for every kilowatt that goes to the servers, another 270 watt is needed for the infrastructure around it. And most of these 270 watt that's needed for the infrastructure is not going to the cooling, because that's a very small amount now. A lot of it is also going to uninterruptible power supply and these kind of things. In other locations, you would see that the PUE is even lower than that in our data centers. So this is the floor plan of the UTM data center, and you see there's a lot of infrastructure belonging to a data center. With the liquid cooling, we have reduced the amount of space we need for the servers. So yeah, there's plenty of space now here. I skipped to the detail how the hydraulic scheme looks like, but I added it to the presentation. So if you're really interested and want to have a closer look at this at a later stage, please feel free to do that. So a few more use cases, and then I can sum up my talk. Another use case is the Deutsche Telekom. They are currently setting up a gaming cloud infrastructure for gaming, which is, of course, for these people like that, a great thing, not to buy the hardware anymore at home, but they can now book it at Deutsche Telekom. On the other hand, it increased the electricity bill of the Deutsche Telekom and the CO2 footprint. So with our technology, we actually help them to reduce the CO2 impact, and we hooked up these systems, and Telekom hooked up these systems to their building infrastructure, reusing the heat of the gaming servers. And one simple rack of only has 10 kilowatts of electrical and thermal power. With each rack, we save cooling costs of almost $3,000 a year and heating cost of 1,800 euros a year. So I added also to this presentation a more detailed look where the energy typically goes. We have a comparison here between the air-cooled system, how that typically works like. I'm not going in all details, but you see that a lot of the electricity comes in, and that's basically converted to air, right? So to warm air. With fans, it's moved out, and then it's going to refrigeration part and generates then waste heat. Even if you have some free cooling going to a dry cooler, it still needs a lot of electricity. So total 86,000 kilowatt hours per year to run such a system. So if you switch to liquid cooling, you immediately see that the electricity is still converted to heat, but the air part is only a small part that goes into air, because most of it is captured directly into the heat, into the warm water. And this warm water can be used then in the heating system during the winter time. And in the summertime, the hot water goes out the door through a lower energy heat exchanger and is then as waste heat released into the environment. But this needs much less energy than an air conditioning system. So that sums up to 62,000 kilowatt hours per year. You see a saving of 26,000 kilowatt hours per year just by switching from air cooling to liquid cooling and heat recovery of the data center. So last but not least, use case is the data center container we have developed. So a modular system that can be placed on places where the energy is generated, like renewable energy, water, and so on, and it can be hooked up to the district heating. And we are proud that we work together with Vattenfall on these systems. So this is designed to fit Vattenfall's need to hook that up in the energy infrastructure to have a very, very sustainable way of using the electricity for computing purposes. On the other hand, converting it to heat and use that in a district heating system. And these data centers can have very high power. It's high performance computing. So they have up to 275 kilowatts per container. and they generate a heat of 63 degrees Celsius. And that's a novus because this is very high temperature level that we can guarantee with our control electronics, with our special cooling units and cooling loops we have developed to fit on top of servers. These are servers from classical server manufacturer like Dell, Lenovo, and others, but also systems we have built ourselves. So our vision, and that's a vision that probably comes more and more true, is that despite the big hyperscales that have the hyperscale data centers, there's room for new technology. And that means there's room for distributed data centers. And these data centers should be connected to renewable energy. And if you do that, you can basically reduce the amount of cabling you need to bring the energy somewhere, because you just place the data center where you have the energy. And then you can place it in locations where you have cities and pipe the energy that is produced by these servers into the district heating system. And with this, you can heat the buildings, and you don't have to need coal or other CO2 emitting energy means to heat those buildings. And the other advantage is if you put the data centers close to the cities to heat them, you also have the data center close to the people who need the services, right? More and more interactive services will come up, and the users will use that. And it's pointless to put all the data across the ocean and back. This is also a waste of energy. So processing them locally, it's much easier. And with some of the big data applications, even problematic. It's sometimes even hard to get all these data that the autonomous driving car is collecting, get all these data saved to a pipe through glass fiber connection, because these are massive amounts of data the camera and all these sensors are producing. So with this kind of general impression and wrap up, I want to close my talk. I motivate you to be part of changing the world. Feel free to contact us and enjoy the rest of the day. Thank you very much.
Thank you, Jens, for that presentation. Very interesting presentation. So you have quite a few innovative, you could say, building or use cases for waste heat inside buildings themselves. I think you're muted at the moment, Jens.
Yeah. No, I'm allowed to unmute now. Okay. So yeah, thank you very much. So yes, indeed. So indeed, almost all of our locations make use of heat recovery, and we started indeed in buildings, even in very small houses, even to do heat recovery, which makes it easy because locally you can directly use it. Now with going with Vattenfall and others to a more elaborated, higher density data centers, we do district heating, and the other level is also in places where the heat is not needed. We are working now on solutions how you can use the waste heat of the data center to drive other processes. For example, to drive an absorption cooling unit to produce cold air, for example, for air conditioning. That could be a means what you can do with that. We are working on a plan now for desalination, so using heat of the surface to produce fresh water from seawater, which might be very interesting for as you can imagine, countries where you have deserts. So yeah, so there are a lot of things you can do once you start going away from this paradigm of air cooling to another liquid cooling means, right?
Excellent. So we have a question here from Stefan Frenzel. So if we can unmute Stefan and let him ask his question.
Hello, can you hear me?
Yes, we can.
Yes.
Hello, Dr. Struckmeier. So basically, I have two questions. So basically, the first one would be about your direct cooling solution. From my understanding, it's at this point of time an individual tailor-made solution, or is it like a standardized product you can sell to the market?
So we have both. so liquid cooling has been around in the past, more for like gaming purposes or for special customers who do high performance computing. So what we have done initially, that we started putting the fans from the servers, from a standard server, and put our liquid cooling technology onto these servers and then selling that to the customers. So you can buy them from us. Okay. But we work now with Dell, Lenovo, HP, because they have now also servers in their portfolio that can be liquid cooled, and we include them in our infrastructure or in the infrastructure model we provide. So far, unfortunately, there's not a general worldwide standard for liquid cooling yet. So if you buy the liquid cooling for Lenovo, it has different connectors than the liquid cooling from Dell. So we are working on the Open Compute project community to set standards for these connectors and for the liquid coolings, so that it becomes completely interchangeable. Exactly. Until now, yeah, go ahead.
Oh, sorry, I interrupted you, but yeah, exactly. This is what I was after. Because at the moment, if you talk about an OCP rack, it's mainly air cooled. But if we could really switch to water cooled as a standardized solution, that would be actually brilliant. And there is a market for it. I'm aware of that.
Okay, so, great. Yeah, so come in contact with us and invite and people are invited, of course, to contribute to the Open Compute project as well. It's, as you know, it's very open. So, and I believe this is the fastest way to get a standard to go to this kind of Open Compute, because going through all the legislation in European and German laws and put a standard there in the ISO, so that takes a lot of time. We have started that as well, this process, but that's complicated and you have to get all manufacturers on board. But I think that's an important thing, because people don't want to have a vendor login, right? So if they decide to go with a Cloud&Heat solution, they don't want to be stuck with us per se, right? So they want to be still remain flexible. So we solve that at the moment with adapters. So you can buy just a Dell system, put an adapter on, and put it in our system. So that's an intermediate step, and I hope the awareness gets more and more, and we know that Europe is at the forefront of being aware that liquid cooling makes sense from the green point of view, from the energy point of view, but liquid cooling makes sense also from the power point of view, and that's something even in the US they see that with the new graphic cards from NVIDIA. They see they have very high energy densities, or the new Intel chips where you have a CPU and a GPU on the same chip. These things are getting so hot that it's very hard to cool them with air. So liquid cooling is now coming more and more in the industry, and that will be a good thing, I think. And we'd like to be part of helping to get this kind of as a standard solution.
So from my understanding, you already involved in the advanced cooling solution subgroup at OCP?
Yes.
Okay. Good. So maybe we can elaborate also afterwards at some point on that.
That would be great. Sorry, what is your name? Or
my name is Stefan Frenzel. I'm also responsible for OCP in the DACH region.
Ah, okay, Stefan Frenzel. So drop me an email. Actually, it would be great, so we can stay we be in contact. Okay,
thanks.
Okay,
perfect.
Thanks, Stefan.
Perfect. Next question is from Steve Pass. So let's go over to Steve and unmute him. Steve, I think you're live with us. Yep.
Hi, yeah, Steve Pass from TC Intelligence. Just curious to understand more about some of the costs involved in deploying this solution. Specifically, some of the case studies you mentioned there's some great savings, but understanding what the costs to deploy the system in the first place and then the return on investment would be really interesting to see.
Yes. So we gained some experience there. At the moment, it is that you have roughly, if you have an existing data center and you want to retrofit liquid cooling into this, that means you have already an infrastructure and you have to put some additional in there. So you have about 10 to 20% extra cost to put a liquid cooling in your data center compared just to buy air-cooled servers. And the depreciation depends very much on the energy prices you're paying. So in Germany, you have high energy prices, so the return of investment you have between 3 to 6 years. If you go to a location with high energy prices, it can be as long as 8 years, and that's typically too long for people, to be honest. So this 20% extra kind of leads that some people say, no, it's not cost effective, but that's for retrofitting in an existing data center. If you build a new data center and you put the liquid cooling initially in there, you can basically do that without no extra cost ab initio. And then it becomes much more attractive to do that. And that's to say with the current water cooling technology. And the problem with this is that it's low volume, right? So less than 1% of all servers in the world are liquid cooled. So that means the air cooling, the massive air cooling things you have on the servers, they are low cost, even though they are massive and complex. And the liquid cooling, that's actually less complex, but it's still quite expensive because of the smaller volume. So we are working on manufacturers and on car component manufacturers in Germany, working with them to use these technologies they use to produce 10,000 or 100,000 of cars, to use the same technology to build the cooling blocks. And then the price of these cooling blocks really goes down. And our goal is to get even ab initio the same price for water-cooled servers than for an air-cooled server. And we have a roadmap for that, and I think that will come, and that will make the whole liquid cooling then much more attractive because there's no extra price you have to pay ab initio. But right now it's more expensive, and that's probably a problem for people if they don't get any subsidies, or if they're not so eager on the CO2 reduction. They either have to say it's okay to wait for 8 years until we have a return of investment, or they might not go with liquid cooling. But we see a strong trend here, and even Open Compute will help us because that will bring down the price as well.
Okay, thanks. I think I'll reach out direct just to see if we can get some indicative costs out of you for a trial we'd like to run in the UK.
Okay, please, yeah. I will. Can you just come in contact with me?
Yeah, sure.
Perfect. Okay, Steve, great. Thank you very much.
And just a quick question for me, Jens. You said you mentioned direct on-chip cooling better than, especially when the chips are of higher density. Air is just not sufficient. At what point does air become really not sufficient? At what density? What sort of rack density?
Sometimes so what we have seen, for example, in your team data centers, we have racks there, the old racks that were 3 kilowatt per rack, right? Now we see with the rack we installed there have easily 20 kilowatts of electrical power and of thermal power. And we see already, if you want to do 20 kilowatts with air, we need massive fans and we need massive cooling needs for that. I would say beyond 10 kilowatt per rack, it makes a lot of sense to go to liquid cooling. And we have done some extreme things. So we have designed a rack that has 200 kilowatt in one rack for a special application, for a special customer, but it's impossible to do that with air. And the other thing you see on the board level, if you look at the newest graphic cards from NVIDIA, the V100 or the A100, you have literally, I'll put my hand here, so a cooling block of this size onto these graphic cards. It's heavy, it's a big thing. If you put liquid cooling on there, we have 1/10 of the height for the liquid cooling. So it's much thinner. So you could put more graphic cards in the same space. And space also costs you money. So increasing the energy density with liquid cooling is attractive with new graphic cards. It's attractive with the new CPUs, and it hasn't been attractive for RAM and for other hard drives and other components because you have little energy coming from these devices. But we had to work also on the liquid cooling for these devices because once you go to liquid cooling, people stay hybrid. So they have liquid cooling for the GPU and CPU, but they still have an airflow to cool the other components. But once you are hybrid, it's more difficult to get high temperature levels and get the 60 degrees water out of it. So if you want to have high temperature levels, the best is to have really 100% water cooled servers. And I've showed you one of those servers we have done 100% water cooled in my presentation. So it's technically more complicated. You have more components water cooled, but it totally makes sense because then the efficiency really goes up. And the biggest point is really the price point, get the price down. If we achieve that or others achieve that together with us, and we should join forces there, then it becomes mainstream, I'm very sure.
Perfect. And the last question here from David, what is energy consumption for pumps and liquid cooling in percentage of IT load?
So the pumps, so what we typically see in our data center is, for example, the main pump that does the liquid, the water from the servers to the building, that's 0.5% to percent of the power that goes to the server goes to the pump. So so it's a fairly small fraction. So that was the pump, and what was the other question? Part of the question?
Yeah, that was just the question. What is energy consumption for pumps and liquid cooling in percentage of IT load?
Okay. Yeah. So what we achieved is a year-round PoE in one of our deployments. We have a year-round PoE of 1.03 or 1.26 is actually the best we have over 1 year in a data center. And there's everything in there, right? The electricity losses of the cabling, the pumps, the lights. However, what is special about these data centers, we have very good electric connections, so we don't have an uninterrupted power supply units there, so we are not losing energy there. But that of course has an influence on the PoE. But these are PoEs you can achieve with liquid cooling, and we have found no ways to achieve that with air cooling, not even with free air cooling. This kind of PoE. Is that answering your question?
Yeah, that does. Thank you very much. Okay, perfect, okay. Jens. I'll give you 30 seconds to finish and sort of tell people where they can go to find more information and how they can get in contact with you. I do think your details are on the slides, which people can download from the handout section in their menu. So, closing comments, please, Jens.
Okay, so feel free, of course, to contact us. May also help joining forces. To be honest, I think this is a bigger step than just the company making some money out of this thing. I think there's some change should go on for the whole industry. We want to help with the change. So don't be afraid to contact us if you have good ideas. We join forces also with competitors. To be honest, there are other companies out there, and we're working with them together, because the biggest step for the environment is if people get aware that there are better solutions than just the classical air conditionings in data centers. And I'm really looking forward that so many people are here together, joining their ideas and joining forces on this effort. So thank you very much for that.
Perfect. Thank you, Jens. Thank you for joining us. Thanks for a brilliant presentation and a brilliant Q&A session. Now I'd like to introduce Birger and Dr. Birger Ober. Birger's been with us quite a while. He'll be presenting on heat recovery in practice. Birger works in strategy for Vattenfall Heat, the heat section in Berlin, and is responsible for data center activities. And he's also a member of the board at the SDIA. So welcome, Birger. Please, opening remarks.
Thank you. Thanks, Mohan, for and organizing this, and thanks for having me. Yeah, what Jens also introduced this a little bit. So please, the use case that Jens mentioned around the data center container that they were building, Cloud&Heat was building for us. Actually, this is the background story behind this pilot project that we're currently running, and of course, we're happy to have Cloud&Heat there as a partner. Mo, I think you need to give me some presentation rights because I'm presenting live and we don't have a video. Perfect.
Okay, perfect.
Yep, so I will mute myself and you have the screen. I don't think you, yeah, I think so. If you move to the sharing section, there you go, there you go.
Okay, presentation mode, then perfect.
All right. Now that we've heard from the basically the operators and also the system manufacturers, let me add a bit from a point of view from a utility. And so, same as car manufacturers and also as the data center industry, we are looking to decarbonize the energy system. You hear that? It's all even in our motto. Our main goal is to become fossil free within one generation as a company, as an energy provider. But if you look at the energy sector as such, you have to discern between two parts basically. So one is the electricity part. That's also what Jens already mentioned this. And on the other hand, it's the heat part. So while we have had some very good successes actually with the electricity part, it is a bit more difficult when it comes to heat. So to put it a bit into perspective, so while we already have very good coverage, or quite good coverage, when it comes to electricity from renewable sources. According to Eurostat, it's in the EU 28, it's 32% on average. But there are also other countries around, like Austria and Sweden, with way above 50% of renewable electricity in their grid, and it's and this is for good reason, because it's technology-wise, it's a bit simpler. The maturity of the technology is very, very good. So when you talk about wind power and the massive wind farms that are being built, that we are building out in the sea, so we have projects above 500 megawatt. Per installation, per wind farm, that's just out in the open sea. And the maturity of the processes of the project development and so on and so forth, it's so good that we're actually able to do this. So this is a big factor. And we also see continued growth in both wind and solar. While solar is not so easily deployable on offshore, but it still has a factor. But there's a big difference when it comes to heat. Electricity is much more universal. It can be transformed quite easily in a voltage, and it's also transformable via direct current or alternating current, and you can easily transport it. Of course, there are discussions around the big transportation lines, but in the Chinese, for example, they do it between big wind farms or big power plants, or sometimes even coal-fired power plants. They have close to the coal mines. They build big direct current power lines, several thousand of kilometers, and transport the electricity at basically zero losses, because the direct current technology is much more efficient over very large distances. And yeah, as said, it's also very universal. So as long as you can plug your cable into your, or can have connection, have a physical connection, have the right power or the right voltage level, you more or less can transport your electricity. That is very different than to heat. And as already was mentioned, the heat sector has a very much lower share of renewable, even though it's also very, very relevant, because 40% of the CO2 emissions stem actually from heat applications, and that is also including heat for industrial processes. But still, the heat is needed in the cities where people are. So the general idea of putting the heat source where people are and where the heat is needed is exactly that. It's you need to have the heat where it's needed. You can't transport it that easily. And on the at the same time, cities are scarce for space. So it's not like space was there in abundance. So there's rarely space for massive solar installations. You can't really put up a big 3, 5, 10 megawatt windmill in the city of Berlin, for example. That's just not doable. But still, you need the heat. And it is difficult to transport, and that's the big difference again. Heat has temperature losses. You do not only need a copper cable to transport heat. You need pipe, you need water, you need to pump it, and you need to clean it. You have to come up for your water losses. You have to precondition your water, and it's quite cumbersome actually to transport heat via long distances. But in cities, it really makes sense. It's central. You can use the grid you already have, and we have been operating the Berlin grid, which is one of the largest in Europe even, for over 100 years. And when you have that grid already, then it does make sense to actually use it. So what we have is we know that we want to decarbonize also the heating sector. Electricity is working well, and we of course keep working on that. But also we need to look at decarbonizing the heat sector. And if you have a heat grid and you want to decarbonize that, you need heat sources that are CO2 free that you can then plug into your district heating network. or in the case, as Karl mentioned earlier in the presentation, if you have a very local heat sink or a heat demand, of course, that's a very viable way to also use your heat. So what are CO2-free sources that are actually usable? So first of all, you could say, let's just put up some PV panels and have them power a heat pump. Then you could have the heat pump that's taking air from the ambient and then puts the heat in your domestic homes. Heat pumps have been around for quite some years. I think there's something like a standard now when you build a new house. But PV uses also space, and a heat pump is not the cheapest way actually to generate heat, because you also have to have maintenance for that and so on and so forth. And then you have solar thermal as a second option. So solar thermal, also solar collector, being put up on the roof, and please don't picture the single homes somewhere out in the suburbs, but please picture the multifamily homes in the city centers. So you have very small roof areas actually for quite a few of tenants in the home. And then you also have the homeowners or house owners that are not too happy when you ask them for the space on their roof, because what is happening also with densification in domestic homes is that they of course like to every now and then add another story on their home, on their house, to just have more space to rent out and to earn more money. So they're very reluctant in general to give away these installations or the roof space for solar installations for 10 years plus, for instance. Then you have something like that's referred to as TPI, and TPI means third part integration, meaning you take in heat that is being there anyway, mainly from industrial processes, chemical processes, and also something like bakeries, basically. And what you can do there is, of course, connect everything that you find, but this is very stable. So you need, of course, the heat where you need it, and you need to connect it. And what normally does not happen, that overnight you turn around and find a new oil refinery in your backyard where you can use the heat from. That just doesn't happen. And so bottom line is, if you have such a source in your vicinity, you have already connected it, and if there's just nothing, then most likely there will nothing turn up in the near future. Then you have, of course, data centers, as mentioned also before, and the data centers are a bit of a subset of TPI. Of course, data centers could be a third party, but the big difference for data centers is that they grow, and that you see more and more capacity, more and more electricity is being used in data centers. And that's the big differentiator, and that's why we've started to look at this also. You've heard this story also, just to do very quickly. We have seen the massive growth in electricity consumption in the early 2000s. You have a bit the hyperscale efficiency boom, you could say, and between 2008 and those years. But now the growth started to kick in again, especially for the new applications, also decentral, everything that Jens said, the 5G, autonomous driving, IoT and gaming, and all that sort of applications that are coming our way. That then need the capacity, and that capacity, when it's being run, is generating heat again. So what we have so far, so we know that we want to decarbonize the heating sector. We know that data centers are there already, are growing, and also in the cities. You might ask, okay, what's the big deal? Why not just do it, and why not connect them? Then I revert to what I said earlier. It's a bit more difficult than for electricity. So what is important to heat network operators. Basically, it's three things. It's the temperature of the heat you can get, it's the pressure, and it's location. And temperature is a rather easy one. You just need, if you connect a water pipe to district heating network and you have too low pressure, the water just flows the different direction or the wrong direction. Of course, it's just a pump and a good layout, but that's really solvable. What's a bit more difficult is actually the temperature. And Jens and I have the same source for the pictures. What is happening with the standard data center is, and these are data centers that are already existing in the big cities, is that they have air-cooled cooling systems, and they give the heat out at the exhaust, if you will, at 30 to 35 degrees C. That doesn't get me as a network operator, district heat network operator, nowhere. That's really actually waste heat. With a system that has been developed by Cloud&Heat, actually, we don't get a 30-degree warm air, we get 60-degree warm water, and that for us is a game changer because that's already in the temperature level where our return flow is, and that is already when we can actually utilize that heat to put this in our district heating grids. And of course, the direct hot water cooling system also reduces the overall power that is needed to run the server overall, and that's of course interesting for us. So then as a third part, that's the location. I think that's a rather interesting one because you have something that you can use as a differentiator, and that's the latency issue. So if you have an application where you are in need of very low latencies, meaning anything that needs very quick response when you interact with it, so be it 5G applications, autonomous driving, IoT, streaming, gaming, then you as a data center operator are in need to be exactly where your customers are. And looking at the density of the population, that is the city. So you need capacity within the city when you have latency sensitive applications. But this comes at a price. In the city, electricity is scarce, space is scarce, and prices are high. So that's why you only would want to do this if actually it is worth it for your application. That is then that is the capacity that's latency sensitive, but then there's the hyperscaler part is much less sensitive to latency. So applications, social media, web or e-commerce, that's just not too critical. If your Facebook timeline loads a tenth of a second later or earlier, who really cares? And also they're very clever about the algorithms they use and what they present to you and so on and so forth. So that's why these data centers from the real big ones are way out in the Scandinavian north. Because it's just cheap, the cooling costs are low because they can use free cooling, which is rather efficient mostly all year long. And that's where they are going, the very big companies, as long as they can. But still, if you are out in the in the Scandinavian north, still if you use free cooling, still you're not putting the heat to a good use. You are using most likely hydropower, and you don't heat up city, but still it's something that you could use in a different setup. And to sum this up a bit, what I think what you have is when you have latency relevant applications, this is only one aspect, the latency. It could also be HPC applications, because we also saw that with water cooling you can have much higher densities, which are then very well usable for something around AI, where you need a lot of high density equipment, for example. So if you have these latency relevant applications, these will be most likely in land and data centers, data center capacities that are on urban areas. And if you have a well-designed cooling system and a good system energy system integration, you actually can achieve good heat recovery. And if you combine these two, you reach quite a bit in terms of what we're discussing here, being more sustainable. I mean, we as a network operator can replace fossil fuel with heat from data centers. Essentially, we're taking the waste out of waste heat, because it then all of a sudden, if done right, it becomes a product. You can reduce the overall electricity that's then needed for the data center operation. And in some you have a low latency and high performance, and it's even competitive in price. And I'm just saying that to repeat what Jens said, because we just know from our pilot project that we're just running in just south of Stockholm, where we deployed 2 of the data center containers from Cloud&Heat, and we do also have water-cooled OCP racks in there. To Stefan, maybe that's interesting for you, to actually showcase this. So what can be achieved if the company that is building these, so us in this case, having control of the electricity grid, the heat recovery system, and also the IT infrastructure, what can actually be done in terms of efficiency in that case. And of course, we're happy to invite everybody that wants to take a look what we're doing there, and maybe work something out to something together there. And it's just not me saying this, it's also our Germany head, Tumo Hataka. He's also the head of the business area heat, and he's also quite certain, as you can see from this quote, that he's very much convinced that data centers will play a role in the heat supply in the future. With that, I'd like to close, and of course be happy to take your questions.
Thank you, thank you, Birger. Really interesting presentation. I have a question to start with. How does the development of district heat grids, they often say 3rd generation, 4th generation, and so on. Do you see that development happening across Germany in particular, where the input temperature is the required input temperature is coming down?
Yeah, they are, and new developments are actually at a low exergy grids, so-called low X grids. If you have the choice, then you normally do that. But it rarely happens that you just start a district heating grid from scratch. So those projects are around, and I'm not even aware of all of them, most certainly. But most of the growth in district heat actually happens in addition to existing grids, and the nucleus of or the nuclei from existing grids are quite old. And when you have a connection to an existing grid, then you're more or less, for efficiency reasons, bound to the system parameters that you have in the old grid, and those are run at 120 degree plus in the forward temperature, and that's where the problems begin, actually. So if you have a low X grid, and I mean, Karl presented it earlier today, that's of course brilliant. If you have such a low temperature heat sink where you can use the heat in a better way, that's brilliant. That's a perfect match. But then again, it's the size of the heat sink. No, it's in Berlin, it's 1500 megawatts. I don't know, I think Karl talked about 1 megawatt or 1.2 or something.
And how would data centers locate these low exergy grids? Because I presume they're not well publicized.
No, I think that's one of the big advantages of the SDIA, and that's basically that was one of the ideas behind it. If you are a data center operator, it's very difficult for you to also develop a new quarter, a new living quarter, basically, to say, wait, by the way, I'm planning a new data center, and oh yeah, now since I have waste heat, that's enough a reason for me to also develop the quarter around it, because I then can sell the heat to my branch that is now offering housing for people. You won't do that. You need somebody to bridge the gap between the industries. So yes, of course, this could be doable, and it's not rocket science, but experience tells us this does not happen because, yeah, it's complicated, and that's why you need a catalyst for.
Mm-hmm. Question here from David: is 60 degrees the minimum temperature to work with district heating, or can it be lower?
So what's really interesting for using waste heat in district heating is that if you can omit the heat pump, especially in Germany because of the high electricity prices, if you utilize a heat pump, then your specific prices just go up, and you don't want to do that. So as long as your district heating return temperature is higher than the waste temperature, you're sort of okay. It's not brilliant still, but at least you are in a position where you can actually think about it. So much lower doesn't work, and the return temperatures of district heating grids, at least the big ones, are it differs. When the very good ones, the bit of isolated ones, very well steerable ones, so meaning newer grids, are at end of 50, but also in occasions you see district heating return temperatures of close to 60. And then it's also very, very close, because you always need a temperature gradient to make this work, of course.
Mm-hmm. And then we have two questions here from Jamie Comella. So let's see if Jamie can, if we can unmute Jamie so she can ask them, or he can ask them himself. Jamie is still self-muted. I'll read the question until they're ready. What about CO2 emissions from data center facilities? Do you think there should be included in the EU? Do you think they should be included in the EU emissions trading system?
Oh, political question. To be fair, I mean, everybody is being included more and more, and we as an energy utility are for the most part. And if the overarching goal is to reduce CO2 emissions, and it doesn't happen by itself, which it obviously doesn't, you need an incentive, and something like a tax, it's nothing else, on CO2 is a way to go, definitely, yes.
And a second question from Jamie: are the utility companies ready to invest in a heating network able to collect the waste heat of data centers and other products with similar temperature levels? And it sounds like the answer is yes. Are the utility companies ready to invest in a heating network able to collect the waste heat of data centers and other producers with similar temperature levels?
Actually, it's changing. It's changing. So what I see, looking 2-3 years back, looking at conferences I've visited, the notion always was, if somebody wants to supply heat to my network, he should take care that the temperature fits to my parameters. Full stop. So there was very little flexibility, and also look at own systems. How can we optimize our own system to actually take that heat in? And I see that softening quite a bit. But heat networks are quite, they're not so straightforward as it might sound. It's really difficult, and it's not only pressure and location, temperature. You also have to think about where is the heat being supplied. You sometimes have 20, 30, 40 meters height difference in your geography. That sometimes makes it it's sometimes a digital decision whether it makes sense or not, because you just have to install an extra pump to bridge that gap over a small hill, basically, of 30, 40 meters that could kill such a project. So I see movement in that direction because, as mentioned, utilities have a drive to decarbonize. But yeah, right now the economy behind it sometimes is difficult. Let's just say it. That's how it is.
Interesting. And then a clarification here from Emma Fryer. Emissions from data centers are already included in the EU ETS, but it only covers scope 1. So it's only emissions from backup generators, not energy consumed from the grid. Question here from Stefan. So Stefan will unmute you and you can have a go at the question.
Hello, can you hear me?
Yep.
Great. So basically, my question would be using, let's say, the waste heat from data centers. To my understanding, Dr. Ober, in Germany, especially in the western part, there is no big district heating system or grid like in other countries.
No, especially the west of Germany is full of district heating grids. So the Rhine-Main area, it's full of district heating, especially around Frankfurt. There is a combined grid, and that's the largest in Europe. I don't know. They planned a connection of several district heating systems, and the combined one would be the biggest in Europe. I don't know if they finished that project, but the west is full of it.
Basically, why data center providers are not using or reusing the waste heat from the data centers is basically in terms of cost, because they need to use heat pumps to increase the heat from 35 to 80 degrees, right?
Yeah, basically it's costs. So it's you need to find somebody to pay for the integration costs, and your district heating operator is not in need of several new heat sources. The power plants are already there, so you have your own heat sources that you have under control, and now you have a new project coming your way where you want to include data center waste heat. But if you have your own capacity already that's ready for operation, you know all the costs and so on and so forth. And then sometimes the data center operator wants to sell you the heat, so he wants to see money from that. For the most part, all the projects I know of were killed or at least looked at, but we decided on in a negative way due to costs and project risks. How much heat does the data center really supply? How secure is that? And so on and so forth. So that's super difficult, and that's basically the reason why we decided we need to do this ourselves. We need to have everything under control. So we didn't set out to become the next cloud provider, but now we're offering bare metal services because we need to have everything under our control to show that this actually works.
Okay. So basically, your recommendation would that be, instead of using that heat for a district heating grid or system, to use that heat regardless of the cost now at this point of time for a nearby, let's say, school or kindergarten or public swimming pool instead?
If you find these applications, yeah, that's perfect, because it's technologically it's easier, and it will be more cost efficient because you don't have to go over the hurdle of the high temperature. And this is also a question of scale, and then again of technological flexibility. So if you have I don't know, a hyperscale installation, let's say you have something like a 50 megawatt data center around, and they are willing to actually full-heartedly engage in a project where you can make this and even get some funding in place. I think this could be done in a good way and also in a way that actually makes sense. But that also requires some flexibility on both sides. And also looking at it from an experience point of view, flexibility in these areas is, yeah, it's not in the DNA. Let's put it that way, because both industries have been working in the past independently, meaning the heat and the data center operators have been working independently quite successfully. They have very little incentive to actually shake their foundations. Yeah, again, also a part of the reason why back then we formed the STIA to actually tackle these questions.
So yeah, many thanks for this information. Maybe we can touch base in a bit more detail later on. If okay, I reach out via LinkedIn, and then we can maybe continue with it.
Yeah, happy to.
And so let's just maybe touch on those integration costs. So there are integration costs from two sides, aren't there? You have the utility side, or the district heating grid side, which is reliability, paying for it, potentially heat pumps are required. But then from the data center operator's point of view, they're thinking, well, what if the district heat grid can't take my heat? I still have to provision for the worst case scenario, which is cooling as though that heat weren't required. So that's exactly where the crux of the argument is, isn't it? It's the integration.
Yes, it's costs, and you could also say it's the value of the heat. That's difficult because you need some sort of price actually to calculate projects like these. And if you as a data center cannot guarantee that you are providing the heat to my network, because you don't have your customers under control. If they decide to go on winter holidays for 2 or 3 weeks and don't run any services, then your heat output will drop. There's nothing you can do about it, unless you're putting some artificial load on your on the machines, which is then again questionable. So from a district heating network operator's point of view, it's like, okay, yeah, there might be some heat, but can he guarantee it? No, he can't. And he can't even guarantee the temperature level. So I always have to look at how can I actually integrate it in a good way. And then I need to put new pipes, I have to operate pumps, I have to build the control system. And if the data center fails to deliver the heat, then I need to steer my own grid in a way that it still works, that all my customers are still being supplied with fresh heat. And then if the data center is actually used to supply a new section of the grid, then I still need to make sure that there's enough backup capacity, because nobody can tell me if the data center goes into a power outage. So it's those are reliability, temperature, price, and installation cost. Those are the three hurdles basically for these. And the temperature argument becomes much less difficult if you would be deploying hot water cooling altogether, because then you have already water, you have 35 degree or degree Kelvin more heat or higher temperature. That really changes something. But if talk to all the big ones, all the phone numbers are probably available, and ask them how much in favor they are right now of switching, of shutting their air-cooled capacity down and rebuilding it in a water-cooled with a water-cooled system. Not going to happen. I mean, the buildings that are existing, they are built for 20, 25, 30 years, and they have 90, 98, 99% of the capacity is air-cooled. They will not shut it down and rebuild it with air-cooled systems. Maybe over time, but not in the near future. It's just a matter of money.
And the last question here from David: what about south of Europe? Is there also high temperature for heating?
south of Europe, that would be Africa in my view. So I'm not.
Southern Europe.
Southern Europe. Okay. I am not. I'm not really aware that there are large-scale district heating networks in Southern Europe, because you just need way less heat in the areas. I know some but at least that's northern Italy. But that's as far as it goes. And every time you need you have a district heating grid, you of course think about this kind of setup.
Perfect. I don't think there are any more questions, so I'll leave it there. So thank you, Birger. I want to give you 30 seconds to address the audience, tell them where they can find more information and how they can contact you.
Yes,
and then I'll close the session.
Thanks, Mo. First of all, thanks for your time. Thanks that you were so patiently taking in my thoughts. And yeah, please reach out to me via LinkedIn. Mo also has my contact details. Happy to discuss. And yeah, have a nice evening.
Perfect. Thank you, Birger. So that concludes day 3 of the conference. That concludes, sorry, day 2 of our conference. That's our heat recovery workshop. We were supposed to have another talk, a man called Richard Tozer, who's going to go into detail on generation 2, generation 3, generation 4 district heat grids, but he's unfortunately ill. So that concludes our heat recovery session. Tomorrow, we start on the SDIA's initiatives session. So those are some of the initiatives that the SDIA is undertaking, and I hope to see you all there. It should be a very exciting session tomorrow afternoon. As you still have in your menu bar, you still have the handout section if you still want to grab the last of the slides. Of course, everything will be recorded and uploaded to a plethora of websites after the event. So thank you all for coming, and I hope to see you tomorrow.